Let's now discuss the scenario when the single rotation is unable to restore the balance factor in the permissible range of -1 to 1. In that case, the double rotation is required. As discussed earlier, when a new node is inserted in a left-right manner with respect to the unbalanced node, a double left-right rotation is required. Similarly, when a new node is inserted in the right-left manner with respect to the unbalanced node, the double right-left rotation is required. Let's revisit the tree on the right in the slide. Here, the insertion of a new node 22 has increased the balance factor of node 25 to +2. Note that the new node 22 was inserted on the left of 25 and on the right of node 12. This is a left-right insertion, and as mentioned earlier, we require the double left-right rotation to restore the balance factor. Just to establish the need of double left-right rotation, please take a pause here and carry out the single right rotation at 25 and verify its effect on balance factor of all the nodes in the tree. As you would notice, the single right rotation over 25 does not make the tree balanced. Instead, it makes the right subtree heavy and the balance factor of the new root of the tree becomes -2. Let's now discuss how double left-right rotation restores the balance factor. Consider the symbolic tree on the left in the slide. We use the similar notations as used earlier. Here the circle represents a node and a rectangle represents a subtree. Here X is a newly inserted node. When we walk upwards in the tree starting from X, P is the first unbalanced node in the tree. The left child of P is named as LC and the right subtree of P is named RC. Left child of LC is named LGC and the right child of LC is named as RGC. The left and right subtree of RGC are A and B respectively. Here X is inserted on the left of P and further on the right of LC. This represents the left-right insertion case. We carry out the double left-right rotation to restore the balance factor at P. The double left-right rotation is a two-step process. Step 1 is the left rotation at LC and the second step is the right rotation at P. Let's discuss the step 1, that is the left rotation at LC. As mentioned on the slide, RGC moves upwards and LC becomes its left child. Note that this rearrangement does not violate the binary search tree property as the value of LC is less than the value of RGC. Now we need to adjust A, the left subtree of RGC. As per the binary search tree property, value of nodes in A are greater than LC and less than RGC. So they can be attached on the right of LC without violating the binary search tree property. The resultant tree is mentioned in the middle of slide. Let's now discuss the step 2, that is the right rotation at P. As mentioned on the slide, RGC moves upwards and P becomes its right child. Note that this rearrangement does not violate the binary search tree property, as the value of P is greater than the value of RGC. Now we need to take care of the right child of RGC, that is the subtree B. As per the BST property, the values of nodes in subtree B are greater than RGC and less than P. So they can be attached on the left of P without violating the binary search tree property. The resultant tree is mentioned on the right in the slide. Let's now verify whether or not these steps restore the balance factor at P in the permissible range of -1 to 1. Consider the tree on the left. We assume that before the left-right insertion of node X with respect to P, the balance factor of all the nodes in the tree were in the permissible range of -1 to 1. After the left-right insertion of node X, the balance factor of node P has become +2. That is, the height of LC minus height of RC is +2. Let the height of LC be h plus 1. So the height of RC must be h minus 1. We know that the height of P is 1 plus maximum of height of LC and height of RC. That means the height of P is h plus 2 after the left-right insertion of X. What is the height of LGC and RGC? As the height of LC is h plus 1, one of its children must have the height h. That is, the height of either LGC or RGC must be h. We argue that the height of LGC cannot be h, because if it is so, the height of LC was h plus 1 even before the insertion of X, and the balance factor of P was +2 even before insertion of X. Hence, the height of RGC is h. What is the valid height of LGC then? It must be h minus 1. The LGC height cannot be less than h minus 1, because if the height of LGC is less than h minus 1, the balance factor violation will be present at LC, which is not the case here. Now, what is the height of A and B? As the height of RGC is h, one of its children must have the height h minus 1. That is, the height of either A or B must be h minus 1. We argue that the height of B cannot be h minus 1. Please take a pause here and reason about the same. The height of B cannot be h minus 1 because if it is so, the height of RGC was h even before the insertion of X, and further the height of LC was h plus 1 even before the insertion of X, and that means the balance factor of P was +2 even before the insertion of X. That means height of A is required to be h minus 1. What is the valid height of B then? It must be h minus 2. Please take a pause here and reason about the same. The height of B cannot be less than h minus 2 because if the height of B is less than h minus 2, the balance factor violation will be present at RGC, which is not the case here. The middle tree on the slide shows the resultant tree after the left rotation at LC. As before the rotation, the height of LGC is h-1, the height of A is h-1, the height of B is h-2, and the height of RC is h-1. The new children of LC are LGC and A. The height of both of them is h-1. Hence, the height of LC is h and its balance factor is 0. As this is the intermediate stage of two-step process, the value of balance factor is immaterial. Similarly, the new children of RGC are LC and B. The height of LC is h and that of B is h-2. Hence, the height of RGC is h+1 and its balance factor is +2. As this is the intermediate stage of the two-step process, the value of balance factor is immaterial. Similarly, the new children of P are RGC and RC. The height of RGC is h+1 and the height of RC is h-1. Hence, the height of P is h+2 and its balance factor is +2. As this is the intermediate stage of the two-step process, the value of balance factor is immaterial. The right tree on the slide shows the resultant tree after the second step, that is the right rotation at P. As before, the height of LC is h, the height of B is h-2 and the height of RC is h-1. The new children of P are B and RC. The height of B is h-2 and the height of RC is h-1. Hence, the height of P is h and its balance factor is -1. Similarly, the new children of RGC are P and LC. The height of both of them is h. Hence, the height of RGC is h+1 and its balance factor is 0. We note that the balance factor of all the nodes are restored to the permissible limit of -1 to 1. Further, the height of this subtree is also restored to h+1, which was the height before the insertion of x. Hence, no balance factor violations are introduced upwards in the tree.